Hello everybody and welcome back to MrMiers Math Channel. Today we're starting Chapter 9, which talks about rational functions, and we're going to go over Section 9.2, which is talking about graphing rational functions. Alright, so let's get into it. First, a rational function is a function of the form f of x equals p of x over q of x, so one function over another function, where p of x and q of x are polynomials and q of x cannot equal 0. Obviously can't equal 0 because then our denominator would be 0 and we wouldn't have anything to graph. Right? On the left side we have y equals 1 over x, and on the right side we have y equals negative 1 on x. We start with these. These are the simplest function of this type. So in y equals 1 over x, we can see that the graph exists in quadrants 1 and 3. And then in y equals negative 1 over x, we can see the graph exists in quadrants 2 and 4. Okay, so if our function's positive, our graph is going to exist in those two quadrants. If it's negative, then our graph is most likely to exist in those two quadrants. All right, so let's get to some of the properties. All right, each graph is a hyperbola of with the following properties. The domain and range are all non-zero real numbers. The graph has two symmetrical parts called branches. So each one of those parts of the graph is a branch. And for functions of the form y equals a over x, the value a tells you the shape of the graph. So if a is greater than 0, aka it's positive, like in that first example, the graph exists in the first and third quadrants. If a is less than 0, aka negative, the branches are in the second and fourth quadrant. As the absolute value of a increases, the branches of the hyperbola move farther from the axes. So that's something we'll see throughout our examples. All right, now let's get to the general form of our function, y equals a over x minus h plus k. That's a hyperbola with a vertical asymptote at x equals h and a horizontal asymptote at y equals k. To graph a rational function, we're going to use these steps. We're going to first draw the asymptotes. Okay, those are those boundary lines that we can never cross. Step 2, we're going to plot points on each side of the vertical asymptote, and then we're going to draw the two branches that approach the asymptotes and pass through the plotted points. All right, so let's get into our first example. We have the graph y equals negative 4 on x. All right, so the first thing that we're going to do is we're going to identify our asymptotes. All right, so k would be over here after the function, and then x minus h would be right here. All right, to get the vertical asymptote, all we have to do is set that denominator equal to 0 and solve. And if we do that, we get x equals 0 as our vertical asymptote. All right, so x equals 0 would be this line right here, right on that y-axis. All right, and then for our horizontal asymptote, that's going to be whatever we're adding or subtracting from the overall function, which in this case would be 0. So y equals 0 would be our horizontal asymptote. And since our vertical asymptote is right at that y-axis, for our table, we can just go a couple units to the left and to the right of that y-axis. All right, so that means we're not going to use x equals 0 because we know that this function is not defined when x equals 0. That would make the denominator 0. So what we could do is put 0 right here, draw a little line through it, and now write some negatives and some positives, and we'll just see how this shakes out. I'm choosing some values that are going to give us some relatively nice and neat output values. So I'll start with negative 4. Obviously, if we have negative 4 on negative 4, that would give us 1. We have negative 4 on negative 2, that would give us positive 2. If we have negative 4 on negative 1, that would give us 4. And then let's move into the positives. Negative 4 on positive 1, that would give us negative 4. Negative 4 on positive 2, that would give us negative 2. And then negative 4 on positive 4, that would give us negative 1. let's plot these values. Change the color here. So we have -4, 1. We have -2, 2, -1, 4, 1, -4, 2, -2, and 4, -1. All right, now these are the asymptotes, so this graph is going to get closer and closer to that line, but never actually touch it. And I'll do my best to approximate the general shape of this graph. There we go. So A in this case was negative. Okay, so that means that this graph would exist in the second and fourth quadrants of the coordinate plane. All right, let's move on to the next one. In example 2, we're graphing the function y equals 10 over x plus 3. First thing that we're going to do is find the vertical asymptote. So the vertical asymptote, to find that, all we got to do is set that denominator equal to 0 and solve, and we would get x equals -3. That kind of looks like a division sign, so I'm going to undo that. There we go. And now to find the horizontal asymptote, we check the equation, see if there's anything listed after the function. There's not, so the horizontal asymptote is y equals 0. So now let's graph x equals -3. That would be right here. And then y equals 0. That would be right here. And now let's make our table. So we know at the vertical asymptote, that's the value by which our function is undefined. So now we're going to choose some other values. All right, so we can be careful about the values that we choose. If we're not careful about the values that we choose, then we're going to deal with a lot of decimals and maybe values that are really close and don't give us a good overall shape of the graph. So I'm going to be relatively careful about the values that I choose. I'm going to start with -8, and -5, -4, then -2, -1, and +2. And you'll see why I'm choosing these values specifically. All right, so -8, if we plug -8 in, that would make the denominator -5. So the reason I plugged -8 in is because then we would have 10 over -5, which would give us -2, a nice easy value to plot. All right, for -5, I chose that value because -5 plus 3 is -2. All right, and then we'd have 10 over -2, which is -5, another easy value to plot. All right, if we plug in -4, we'd have 10 over -1, which would just be -10. All right, now moving on to the other side of the asymptote. If we plug in -2, -2 plus 3 is 1, so we would just have 10 over 1, or just 10. If we plug in -1, we would have 2 in the denominator. That'd be 10 over 2, or 5. And then if we plug 2 in the denominator, we'd have 10 over 5, which is 2. Okay, now we're going to plot these values. So starting with the -8, -2, -8, -2 would be approximately right there. -5, -5 would be right there. -4, -10 down here. And then -2, 10, right at the top of our graph there. -1, 5, and then 2, 2. Oops, right there. All right, so now we're going to follow these points so that we can plot our graph. It might not be the best sketch in the world, but at least it gives us an idea for the shape of this function. All right, and once again, a is positive here, so that means it exists not technically in the first and the third quadrant, but in the first and the third quadrant respective to the axes. All right, moving on. This is our first example where we're going to have we're going to have some horizontal asymptote. So our vertical asymptote, I always like to start with that. Remember, we're going to set that denominator equal to 0 and solve. We get x equals -1. And then our horizontal asymptote is whatever we're adding or subtracting to the overall function right here. So that's y equals -1. So let's plot those asymptotes. Now let's make our table. Right in the middle, I'm going to put that vertical asymptote. Remember, that's the value by which this function is not defined. And then we're going to move to the left and to the right of that vertical asymptote and plug in some values that might be good. Okay, so we have 1 in the numerator. We just want to figure out, okay, what are some values in the denominator that we could have that would be easy to plot. Now, I'm only going to plot 2 values on each side of the vertical asymptote here. So I'm going to plug in values -3, -2, and then 0 and 1. So -3 I picked because that would make the denominator -2. So then we would have -1/2 minus 1, and that would be -1.5. All right, if we plug in -2, then that makes the denominator -1. So we have -1 minus 1, which would be -2. All right, then let's plug in 0. So we would have 1/1 minus 1, which would just be 0. And then if we plug in 1, we'd have 1/2, or 1/2, minus 1. So -0.5. All right, let's plot these values. -3, -1.5, that would be about right here. -2, -2, that would be approximately right here. We have 0, 0, and then 1, -0.5. All right, so you can see that since A is positive, it's going to be on the top right and bottom left of these axes. And then also since A is 1, it's going to be really close to the intersection of between these two axes. So the shape is, of course, going to follow these points. But really nothing super spectacular about the shape. They're really close to the axes, or the asymptotes. I said axes before, I meant asymptotes. And not much happens. It just gets closer and closer to those asymptotes without touching it. All right, on to the next one. All right, this is where we get a little bit more diverse values. So first, the vertical asymptote is going to be x equals 1. Set that denominator equal to 0. Next, the horizontal asymptote is going to be y equals 2. Let's draw those. Here's the vertical asymptote. Here's the horizontal asymptote. Now let's make our table. Put that vertical asymptote right in the middle. Now we're going to just choose some values to the left and to the right. I'm actually going to plug in a bunch of values here. -5, -2, -1, 0 on the left side of the asymptote, and then 2, 3, 4, and 7 on the right side of the asymptote. If we plug in -5, we get 2.5 out. We plug in -2, we get 3, -1, 3.5, 0, 5. If we plug in 2, we get -1, 3.5, 4, 1, and then 7, 1.5. All right, we can approximate these values on our graph and then graph our function. So we have -5, 2.5, -2, 3, -1, 3.5, 0, 5. We have 2, negative 1, 3.5, 4, 1, 4, 1, whoops, then 3.5, not negative 0.5, right there, there we go, and then 7, 1.5. There we go, okay. All right, and let's draw those branches once again. All right, and there's our hyperbola. Sorry, our rational function. Last example is just talking about the domain. So the domain of this function. So the domain would be all the possible values that we could plug in and actually get an output value. So if we take a look at the example 3x plus 2 on x minus 4, there's one value that we wouldn't be able to plug in, and we could find that value by just setting the denominator equal to 0 and solving, and we get x equals 4. So the domain is all real numbers except for 4. All right, so if we take a look at the next example, we've got a couple different problems here. All we have to do is just set the denominator equal to 0 and solve. So negative 9 would make the denominator 0, so that means we can plug everything in except for negative 9. All right, one way to write this, real simple way, is just x can't be negative 9. That's it. That's all we got to do. Nice, short, and sweet. All right, same thing for number 2. If we set 2x equal to 0, we'd get x equals 0, so x just can't be 0. If we set 2x minus 6 equal to 0, we just get x cannot be 3. All right, if we set 3x plus 1 equal to 0, we'd get x equals negative 1/3. So that means we can plug in anything, just not negative 1/3. All right, folks, that's it. If you enjoyed this or found this helpful, like, share, subscribe. Thank you, and have a great day.